Today, we are going to delve deep into one of the most fundamental and powerful concepts in Go programming, pointers. What is a pointer? Let's break down this diagram to understand what a pointer is and how it works. First, look at the large rectangle labeled memory. This represents a section of your computer's memory, with different memory addresses shown inside. Notice the red box in the middle, ending with 08. This is a specific memory address where we've stored a value. Below this address, you see a green box with the number 42. This is the actual value stored at that memory address. Now, let's talk about pointers. See the purple box at the top? It says P with address ending 08. This is our pointer variable, P. A pointer is simply a variable that stores a memory address. The arrow from P to the memory address shows that our pointer is pointing to this specific location in memory. On the right, we have a yellow box with an X. In Go, the AND operator gives us the memory address of a variable. So, an X is pointing to the same memory address as our pointer, P. Lastly, look at the pink box on the bottom right labeled P. In Go, the asterisk operator is used to dereference a pointer. This means it gives us the value stored at the memory address the pointer is pointing to. That's why we have a dotted line from asterisk P to the value 42. To summarize in Go code, X is equal to 42 creates a variable X with the value 42. P is equal to and X creates a pointer P that stores the memory address of X. Asterisk P would give us the value 42 as it dereferences the pointer. Pointers are powerful because they allow us to directly manipulate memory, which can lead to more efficient programs and enable certain programming patterns that would otherwise be difficult or impossible. Let's explore the AND asterisk operators in Go and understand pointer types. In our first example, we start with X is equal to 42. This creates a regular integer variable. Then we have P is equal to an X. The AND operator gives us the memory address of X. We call this the address of operator. Now P is a pointer to X. Next, Y is equal to asterisk P. The asterisk operator here is the dereference operator. It says, give me the value at this address. So Y gets the value that P points to, which is 42. Finally, asterisk P is equal to 24. We are using asterisk again to change the value at the address P points to. This actually changes X to 24. Now, about pointer types. In Go, pointers always have a specific type they point to. Asterisk int is a pointer to an integer. Asterisk string is a pointer to a string. Asterisk struct is a pointer to a struct. This type safety is important. It means Go won't let you accidentally treat a pointer to an integer as a pointer to a string, for example. The power of pointers is that they let us indirectly access and change values. This is super useful when we want to modify variables in functions or work with large data structures efficiently. Remember, AND gives us a pointer, and asterisk lets us work with the value a pointer points to. And every pointer in Go has a specific type it points to. Key points. AND gives the address of a variable, creates a pointer. Asterisk dereferences a pointer, accesses the pointed to value. Pointers have specific types, asterisk int, asterisk string, etc. Go ensures type safety with pointers. Pointers and functions. Let's walk through this diagram to understand how pointers allow functions to modify values outside their scope. We start with our value variable in memory, initialized to 5. When we call modify value and value, we are passing the memory address of value to the function. This is what and value means. It's getting the address of our variable. The modify value function receives this address as a parameter x of type *int. This means x is a pointer to an integer. Inside the function, we perform our calculation *x is equal to *x*2. The asterisk here is dereferencing the pointer, allowing us to access and modify the actual value it points to. This calculation directly modifies the value in memory. We are not creating a copy, we are changing the original value at its memory location. After the function call completes, we can see that the value in memory has changed from 5 to 10. Finally, when we print the value, we see the output is 10. This process demonstrates the power of pointers in Go. By passing a pointer to a function, we can modify variables that exist outside the function's scope. This is more memory efficient than passing large data structures by value and allows for direct manipulation of data. Remember, when you see an asterisk in a function parameter like *int, it means the function expects a pointer. When you see an ampersand like and value, it means we are getting the address of a variable to pass as a pointer. Understanding this flow is crucial for effective use of pointers in Go, enabling you to write more efficient and powerful code. Pointers to structs. Let's walk through this diagram step by step. We start by creating a person struct in memory. It has two fields, name set to alias and age set to 30. Next, we create a pointer to this struct. In Go, we do this using the ampersand operator, p is equal to and person. This gives us a pointer to our person struct. Our pointer, p, is of type *person, meaning it points to a person struct. It's now referencing the memory location of our original struct. Here's where it gets interesting. In Go, we have two ways to access and modify struct fields through a pointer. We can use p.age is equal to 31. Or we can use *p.age is equal to 31. Both of these are equivalent in Go, thanks to its syntactic sugar. When we modify the age using either method, we are directly changing the value in the original struct. We are not working with a copy, but the actual data in memory. After the modification, our person struct in memory now has the updated age of 31. This diagram illustrates a key feature of Go. When working with pointers to structs, Go allows us to use the dot notation, p.age, as if we were working with the struct directly, even though we are using a pointer. This makes our code cleaner and easier to read. Remember, using pointers to structs can be more efficient, especially when working with large structs, as we are not copying the entire struct when passing it to functions or making modifications. Understanding this concept is crucial for effective Go programming, especially when you start working with methods and interfaces, where pointer receivers become important. Slices and maps, hidden pointers. Let's explore how slices and maps work behind the scenes in Go, focusing on their hidden pointer nature. On the right, we have a slice. Notice it's made up of 3 parts. A pointer that points to the actual data. A length of 3, which is the number of elements currently in the slice. A capacity of 3, which is the maximum number of elements the slice can hold without reallocating. This structure is what allows slices to be flexible and efficient. On the left, we have a map. It's simpler in appearance but similar in concept. The map itself, map1, contains a pointer. This pointer points to a hash table, which is where the actual key value pairs are stored. In our example, we have one pair, A1. Now, look at the bottom. We have 2 functions, modify slice and modify map. The dotted lines show that when we pass a slice or map to these functions, we are actually passing copies of these structures. Here's the key point. Even though the functions receive copies, they can still modify the original data. Why? Because they're working with the same underlying data through these pointers. This is why in Go, you can modify slices and maps within functions without needing to return them or use explicit pointer syntax in function calls. It's a hidden pointer mechanism that makes working with these data structures more convenient and efficient. Remember, when you're using slices and maps in Go, you are implicitly working with pointers, even if you don't see the and or asterisk symbols in your code. This hidden pointer nature is what gives these types their power and flexibility in Go programming. Pointer receivers in methods. In Go, you can define methods on types. When you define a method, you can choose whether the receiver, the type the method is defined on, is a value or a pointer. Using a pointer receiver allows the method to modify the receiver. It's also more efficient for large structs, as it avoids copying the entire struct when the method is called. In our example, increment is defined with a pointer receiver. This allows it to modify the count field of the counter. Nil pointers and safety. A nil pointer is a pointer that doesn't point to anything. In Go, pointers are initialized to nil by default if you don't assign them a value. Attempting to dereference a nil pointer will cause a runtime panic. That's why it's crucial to check if a pointer is nil before dereferencing it, as shown in our example. This nil checking is a common pattern in Go and is part of writing safe and robust code. Memory management and pointers. Understanding pointers is crucial for effective memory management in Go. While Go has a garbage collector, knowing how and when memory is allocated can help you write more efficient programs. When you create a value in a function and return a pointer to it, Go will automatically allocate that value on the heap rather than the stack. This ensures the value persists after the function returns. In our example, createLargeStruct returns a pointer to a large struct. Go recognizes that the struct needs to outlive the function call and allocates it on the heap accordingly. This automatic escape analysis is one of the ways Go simplifies memory management while still giving you the power of pointers. As we wrap up our discussion on Go pointers, let's review the key concepts we've covered. Pointers store memory addresses, not values. Remember, a pointer is essentially a signpost pointing to where data is stored, not the data itself. The AND operator creates a pointer. We use AND to get the memory address of a variable. This is how we create pointers. The asterisk operator dereferences a pointer. When we want to access or modify the value a pointer is pointing to, we use the asterisk operator. Pointers enable indirect access and modification. This is the power of pointers. They allow us to indirectly work with data, which can be very efficient. Go uses pointer types for type safety. Pointers in Go are always typed, like *int or *string. This prevents errors from misusing pointers. Pointers are useful for efficient data handling and function operations. They're especially helpful when working with large data structures or when functions need to modify their inputs. Nil pointers represent uninitialized or zero pointers. A nil pointer doesn't point to anything, which is Go's way of representing a zero or uninitialized pointer. Always check for nil before dereferencing. This is a crucial safety practice to prevent runtime panics in your code. Understanding these concepts about pointers will significantly enhance your Go programming skills. Pointers are a powerful feature of Go, allowing for efficient and flexible code, but they must be used carefully and thoughtfully. For any question, please write in the comment box. Thanks for watching.